but it's totally gaming the system. So, okay, let's talk big picture about what we've done and where we're going in physics. So we have 7 lessons in this unit. We've actually blown all the way up through to number 5 already, which is good. We're going to slow the pace down after today because I've kind of been doing a lot of lecturing and I need to give you guys some time to work. So plan is going to be tomorrow's a work day. I had originally scheduled Monday to be a quiz. I want to pull that back because I don't want to put you guys in a scenario yet where you're maybe not ready yet. So let's do Monday as a work day as well. And then let's do the quiz on Tuesday, lab Wednesday. Does that work? We could flip lab and quiz if you want to. I don't know whether there's any rationale to doing one before the other. But I think it makes sense to do quiz the first day of the lab the second day. But if you guys really believe that it makes sense to flip them, we could. I really don't care. We've basically covered, otherwise, they're like the first half of our unit. I know it's not exactly equal amounts because we've done 5 lessons as of today, and then we've got 2 left afterwards. But the first half essentially is all about Newton's laws, basically. So we started our first day talking about just forces in general, like what is a force? It's a push or a pull. And then we talked about his 3 universal laws of things like 1, objects in motion stay in motion, objects at rest stay at rest, unless there's an unbalanced force. So that's inertia. 2, the main formula that we kind of start with, the net of all forces is equal to mass times acceleration. Then yesterday we talked about, was it yesterday? 2 days ago. We talked about his 3rd law, the retaliation principle, where there's an equal and opposite reaction. Today, I'm just going to add one more little twist in here. And some of you, I think, are even ready for this based on your assignments. If I give you a question, I'm just going to make one up real quick here. Right where I can see. If I give you a question where you're being asked to like do a free body diagram on an object, and you do things like gravity's downwards and normal forces upwards, and maybe there's a tension pulling it this way, and there's a friction pulling it backwards this way. For the most part, I've just been telling you what the friction value is. But what happens if we actually have to calculate how much friction there is based on another calculation? Does that make sense? And so today that's this topic here. It's not a whole lot more, it's just adding one extra little step to our puzzle solving. So if you're able to solve all the puzzles up till this point, today I'm going to show you a formula for friction. And you can actually even find it on your formula sheet if you've got it nearby. It looks like this. The force of friction is equal to this funny looking U times Fn. So this is the last thing we're going to do. We're going to add in a formula so that if I don't tell you the force of friction, we can actually calculate it as well. Does that make sense? It's not all that hard. It's just one extra little twist. But I think you guys are probably picking up on how this physics sort of thing works. Individually, I don't know that each individual little bit of physics is all that hard. What makes it challenging is that physics is monumentally large, right? You do this to get this answer, then you take part of that to do this, part of that to do this, part of that, and then you finally solve what you're looking for. But at the end of the day, you have like a full page worth of work, right? Which is kind of new because you probably haven't ever done questions that are so big in scale. Is that kind of a fair thing to say? So all we're doing today, though, is just adding one extra little step in the chain. Okay. So, by the way, after we finish this section here, the next section, although it is kind of related, is going to be a little different. We're going to talk very specifically about gravity, and not about gravity so much on Earth, but then we're going to talk about how gravity affects celestial bodies. Do you guys know what I mean when I say celestial bodies? Say that. Yeah, planets and suns and stars and stuff like that. Yeah. So it still involves forces. It involves the force of gravity. So there is a link between them, but the questions will be very, very different, right? Rather than drawing a free body diagram of a box on a slope, we're now talking about why the moon goes around the Earth and why the Earth goes around the sun and that sort of stuff. So it's still forces, but it's kind of a bit of a break. Does that make sense? So that's kind of our next little while. We're going to finish up this section on more, I don't know, Earth-sized forces for the next little while. We'll talk about how to do one last link about friction. Then tomorrow's a work day, Monday's a work day. We'll try quiz Tuesday, see where we're at. Wednesday we'll do a lab. And then going forward from there, then we'll talk about large bodies and forces on gravity. Sound good? I guess we're so excited, aren't we? Okay. Okay, so let's do some notes here. Talking about friction here. Friction basically is a force that exists whenever you have two surfaces in contact with each other. Okay. If we had a vacuum, maybe you've heard this phrase before, this term before in my chemistry class. Like a vacuum is where basically there is an absence of matter. Unless you had that, basically there is going to be friction. So really, we actually can consider a few places to be a vacuum. When we do talk about, like, say, stuff traveling in space, essentially since there's no atmosphere in outer space, that's more or less a vacuum. It's not maybe perfectly nothing out there, but does that make sense? But for the most part, if we're on Earth, there's an atmosphere, there is going to be friction between two surfaces. And I've already kind of talked about this. If your motion is going this way, and someone is either pushing a block or maybe they're even pulling the block, friction opposes motion. Now, how that might look is different depending on the scope of the question. You do need to use your common sense. If you're doing the question where there's a guy who's driving his vehicle uphill, if he is driving up the hill, friction would be going downhill. Does that make sense? But change that around, and rather than having the car go up the hill, let's have the car go down the hill. Well, now the friction is going to be going uphill instead. Does that make sense? So although there's certain forces that I know which way they're always going, like for example, gravity was always down. Normal force is always kind of up, perpendicular to the surface. Downward force is down the hill. Friction opposes motion. So you just got to figure out which way you're traveling, and that's the way that your friction's going. Does that make sense? I've kind of got a picture here just to kind of illustrate at its base level what is happening when you've got friction. Right? And imagine that you've got this box and it's on the surface, right? This is really what it looks like at a molecular level. Things are not perfectly smooth, right? I mean, it would be nice if things really were smooth like this, but if you really zoomed into a microscopic level, it really looks something more like this. Right? And you can kind of imagine that as these two objects, one goes one way, and according to Newton's third law, really the other one is kind of really going the other way, right? They're opposing each other, right? Then isn't there going to be, like this little ridge right here isn't going to catch that one right there, and this one catch this one right here, right? And slowly over time, as they grind next to each other, you even notice this with things like weather erosion of some type, right? Eventually it will smoothen out a little bit, but even the most smooth of surface, even this surface right here, which I think is really smooth, really it actually kind of looks like this if I can, you know what I mean, zoom in close enough. Right? Some surfaces are rougher than others, but really that's the point I want to make here, is that the smoothness of the surface then will affect your friction. Okay. So even though all things do look kind of like this at a base level, for example, if I had my car's tires on pavement, those are two surfaces which are going to be quite rough. In fact, like winter tires are designed to be extra grippy in the wintertime, right? Whereas like the opposite of this might be ice and a hockey blade, like on your skate, right? That is supposed to not have friction so that you can glide. Does that make sense? Because both of those are more smooth, as opposed to my car's tires, which have like grooves in them on purpose to try to add to the friction. So terminology-wise, I need you guys to know two different words then. There's what's called static and kinetic friction. And they'll probably make sense just intuitively based on you guys probably know those words. Static refers to something that's really not moving. Right? There is friction between surfaces that are really not moving. For example, if I try to push this really heavy object, friction is opposing my attempt at motion, right? I'm just not strong enough to push it, right? So there's a certain amount of friction just due to it not moving. But you might recognize that sometimes once you get an object, once you get it in motion, you can actually kind of keep it in motion, if that makes sense. But that's because a different type of friction is taking place, and that's kinetic friction, where it's friction, but it's where the objects are already in motion. Does that make sense? Long story short, I cannot think of a counterexample, but static friction is usually more than kinetic friction. if I'm really trying to push something really, really hard, once I'm able to break through that barrier of static friction, there still is kinetic friction. Thank you so much. There still is kinetic friction, but usually it's less, right? Imagine that you're trying to push your car out of a snowdrift, right? And you're having a hard time getting it out because you got stuck in the ditch and you're pushing, right? Really, at first, the hardest part for you pushing your car is that your car is heavy. Because it's heavy, it's pushing down on the next surface, and you're having a hard time to get it moving, right? But if you and your 5 friends all manage to finally get it going, once that car gets moving, is there still friction? Well, yeah, right? But it's usually less. Does that make sense? So, long story short behind the slide here, I'm going to get off topic here. You need to know whether or not you're looking for a static or a kinetic friction amount. So, is it moving or not? Okay. So static friction, again, is usually higher than kinetic friction because it takes more force to get the object moving. So, okay. Everything will have then a different coefficient of friction. This is something that we're gonna solve for or be given in a question. And the coefficient is this funny-looking U symbol right here. It's a Greek symbol. I actually forget the name of it off the top of my head. I think it's like mu or something like that. But this is known as the coefficient of friction. Long story short, the bigger the coefficient, the more friction you'll have. The lower the coefficient, the less friction you'll have. So I've got a table here that has like some different coefficient values. Right? When you look at some of the ones that are particularly low, like say curling stones on ice, really there should be very little friction, right? You've got a very smooth curling stone. You've got ice which is very slippery. Look how the coefficient values are very low. Right? Whereas, say, copper on copper, if I try to grind one piece of metal next to another piece of metal, that's why I would use the word like grinding in a way, right? Where it's not going to slide very nicely. You can see that it's got a very high coefficient of friction, relatively. Does that make sense? So, it really depends on the surfaces, though. See how I've always got like one word and then another one? It always depends on what the 2 surfaces happen to be. Rubber and ice is different than steel and ice, is different than steel and copper is different, you know what I mean? So it's always dependent on whatever 2 surfaces there are. So here's how this will work. Either I will tell you the coefficient of friction, you will look it up in a table, or it's what you're solving for. Essentially, those are the options. I will either straight up just tell you the coefficient is this, or you'll have to go look it up in some table somewhere. As in this table, possibly. Yeah, so you may just want to bookmark this table. Not on a test. I wouldn't do this to you on a test, but on some sort of lab or assignment, maybe it could come out here. Or, thirdly, this is probably the more common option, you'll just be asked to solve for that coefficient. So, can you guys see, though, that the static friction numbers are always bigger than the kinetic friction numbers? This one's bigger than that one, this one's bigger than that one. Okay, I guess this one's the same, but... Okay, I want to talk about the Magic School Bus episode briefly, because there was a question there that I want to make sure you all understand. At the very, very end of the episode, there's this scene here where they're trying to get out of the book, but the cover of the book falls on top of them, right? And they can't get out. And I think that kind of makes sense to most people, because if I had a book of some kind, and I put an object inside there, right. And let's say I try to tip this. That object isn't moving, right? If I put the object on top, what was the difference there? Was there friction? Well, in both examples, there was friction, was there not? In this first example, sorry, I guess you guys can't see this all as well. So I'm just putting a pen on top of a book, by the way. Putting a pen on top of a book. Is there friction between the pen and the book? And as I tip it downhill, it has the ability to slide, right? But if I put it inside the book, there's friction against the bottom page, right? But when I close it, what have I not done? There's friction on the bottom and on the top. Does that make sense? And as I tip the book the exact same way, now the object isn't moving. Why? Well, like you said, there's now friction coming from 2 different sides. Now, when it comes to the Magic School Bus episode, it actually wants friction against the bottom, because the friction against the bottom is what allowed the tires to have the grip it needs to push the bus forward. Does that make sense? So friction against the bottom page is actually a good thing for the bus trying to move itself forward. If there was no friction for the bus against the surface, it wouldn't be able to do anything. It would just spin its tires and nothing would happen. Does that make sense? Kind of like when they were on the baseball diamond. But it's actually the friction of the top side pushing down on it that becomes an issue. Does that make sense? And that actually is what I want to lead to in talking about this formula here. Because when we want to calculate how much friction there is, the formula I showed you is actually based on this thing right here. It's based on the normal force. The more that something gets pushed down upon, the more friction there would be. Let me give you an example here. Let's say that I want to try to push this chair forward. Can I push it forward? Sure. Why not? I have that ability to, right? Darian, come sit in the chair now. I promise I won't kick you. As he's sitting in the chair, is the surface any different than it was before? Right? But now if I use the same amount of force, he ain't moving. Why?
Jacked.
Exactly, right? But really what he's doing is he's adding more pressure downwards on the surface, right? Just like the cover of the book slamming on top of the bus is pushing downwards, that actually adds more force. Now, it's not Darian's weight, actually, although he is jacked. I mean, he's pretty good. It's actually not his weight that's causing the problem. It's not gravity that's doing it, but it's the normal force of the floor pushing back up on Darian's chair. You can sit down, by the way. Thank you. You made that point. Okay. But it's not the fact that Darian is so jacked that he's so heavy. It's the opposite force of that. It's the fact that the floor, remember how he is pushing down into the floor with gravity? The floor is pushing back up on him. Does that make sense? And because the floor is pushing back up on him, that's causing more pressure for him, makes it harder for me to push him. Does that make sense? So, long story short, the formula here actually depends on your normal force. The more normal force, the more force that the floor is pushing back up on the object, means there's more friction. So, I know we think of it as though a heavier object does that, but really that's the second link. Darian has weight. His weight pushes downwards into the floor. The floor then pushes back up again. It causes these two surfaces to have more pressure between the two of them. Therefore, there's more friction. That makes sense? So at this point here, I think I'm ready to start doing some calculations. And you'll find the calculations are really not that hard. It's just it's one more formula. So here is that formula. To find the amount of frictional force, you need to know the coefficient, which either you'll be given, you'll look up, or you're solving for. And you'll have to know the normal force. Well, the normal force is usually really easy to solve for. You know how in your free body diagrams, I've mostly been focusing on the x direction, but I've been hinting that you need to draw your y direction in? Today we deal with the y direction, because your normal force is usually the complete opposite of gravity. So as long as you can find gravity, you've got your normal force. So, like I said, it's just one more link. It's not an overly hard link, but it's just one more thing you have to do. Before I get to the calculations, just some more illustrations then. I thought tires were a good example when I made these notes. Right? I mean, here's different types of tires. You've got your big tractor tires. Right? You can see, I mean, the huge grooves in there trying to add so that you can have more grip surface area, right? Does that make sense? So that you have more friction, so that if you get stuck in, I don't know, whatever, a big mud puddle, right, you have the ability to get out. Right? But how is that different than, say, this car right here? A race car, although it does want friction between the tires against the surface so it can propel itself forward, in a way, though, it does really want to limit friction too, doesn't it? Because it needs to go as fast as it possibly can. So it does need friction to propel itself forward, but not too much. Does that make sense? Too much grip would slow it down. Right? Chains on snow tires, so that you have the ability to stop if it's snowy and there's no friction, right? And I don't actually remember why I put that picture, but you get the concept, right? Okay, so let's do some examples. Let's get to the math. You've got a piece of wood placed on another piece of wood. So right off the bat, if we have a table that tells us the coefficient of wood and wood, we can go find that value. But I don't believe that's what we're doing here, because actually this time around we're looking for the coefficient of static friction. It actually tells you how much static friction there is. So let's go right to the formula. The amount of friction is equal to our constant times our normal force, right? If I were to draw a quick free body diagram though, wouldn't you hopefully agree that the amount of gravity is going to be counterbalanced by the normal force? They're kind of opposites, right? So sometimes what I like to do is when I work with these formulas, I'll say, well, isn't Fn going to equal Fg? So then I would say, well, my force of friction equals my coefficient times Fg. But what's gravity equal to? Like force of gravity. What's its formula? Mass times gravity, yeah. So you can say the force of friction is the coefficient, my writing's not very good today, times the mass times gravity. I think I have all the values I need now, don't I? Because it told me this, it told me the amount of friction. Sorry, that's the ugliest little U symbol in the world. Let me fix that. Basically, draw a U with like a fancy tail to start. And that's kind of how the symbol's supposed to work. Like that. So we have the force of friction. That was 35 newtons. We're looking for the coefficient of friction. We know mass. We know gravity. While you guys are solving that, I'll reiterate something I've been saying for the last little while. If you ask me what formula to use, ultimately I think this that I've circled here is more or less the formula we used. Is that actually a formula on your data sheet? Well, not by itself. And this is, again, this is where physics kind of goes. You don't usually get just one equation. You're usually taking one equation and like shifting multiple ones together. So, what'd you guys get? It's going to be pretty small, I imagine, like just under 1. Fair enough. Sound good? Good, yeah. So there's the next thing I want to mention here. There is actually no units to a coefficient of static friction. And here's the reason why. This guy right here, his units are newtons. This one right here, his units are also newtons, because they're both forces. If this has to be a Newton unit, and this has to be a Newton unit, this thing right here has to have no units to it whatsoever. So this is kind of a strange time where this comes up, but don't put a unit next to it. Still do sig digs, but don't worry about a unit. Pretty straightforward. Okay, so let's try a harder question. You've got a sled with waxed hickory runners resting on a dry, snowy surface. Find the maximum mass that can be put in the sled if the sled is not to move, but withstand an applied force. And I wrote us a little hint here. On this example here, I need us to actually look up the coefficient of friction. So can you guys head back in the slides here? It's going to be easier for you to do it. Find that table and find me the coefficient of friction for waxed hickory runners on snow. What was that?
Dry snow.
Oh, yeah, good. Dry snow. Is there a difference in the table there? You're going to have two different values. There's the coefficient of static friction and the coefficient of kinetic friction. Which one do we need? Yeah, can you guys tell why? Sled's not moving, right? So what was the coefficient of static? 0.06. So 1 sig dig. Okay. So we have that information. Let's go back to doing a free body diagram. Well, that's not a bad idea just to stay in the habit of. So here's my sled. Again, I like to put the mass inside of it, but I actually don't know the mass. I know it says it's a 5 kilogram sled, but we want to know how much weight we can actually put inside of on top of the 5 kilograms. Does that make sense? Like maybe I weigh 10 kilograms or 20 or 30 or 40. So we actually don't know the mass of this thing just yet. That's ultimately our goal. We're looking for mass. Okay? It says that there's an applied force of 82 newtons. Well, the other forces in play are going to be your normal force, your gravity, and your force of friction. After you do this for a while, you start to skip the first couple of steps. But just for this example here, I'd like to walk you through right from the beginning how this logic would work. If you're stuck on where to start, you can always start with Newton's second law. The net of all forces is mass times acceleration. But is this sled accelerating? It's not even moving. Right? So, I mean, even if it was moving, if it's not accelerating, essentially the acceleration is equal to 0, which means all of this is equal to 0. So the net of all our forces is 0. Well, you could say that your applied force is trying to pull you forward. Your frictional force is pulling you backwards. Well, that has to equal 0. But truth be told, I think most of you will probably just start your work on this next step here. So hopefully this makes sense. But wouldn't it make sense to say that the applied force has to equal the frictional force? So if you'd like to, I don't need you to do anything other than to start here. But this is the rationale as to why. So far, so good? Okay, well, now I'm going to keep manipulating formulas. Your applied force is equal to the force of friction, but we have a formula for force of friction. Force of friction is equal to your coefficient times the normal force. So I could write it as UFM. I guess I will. But what's the normal force going to be equivalent to? The force of gravity. Because isn't the amount of normal force pushing down the same as the amount of gravity? No. Normal force pushing up the same as gravity pushing down? And then to take it one more step further, isn't the force applied then going to be equal to U times the force of gravity is mass times gravity? I don't need you to write out every single step along the way. Honestly, if it were me, and if you're looking at my answer keys, I probably did something like this. I probably started with this. I may have written this one here, may have, and I probably went right to there. But there's a good chance that what I would have done, just to save some time, because you kind of get used to it after a while, is I would have started with this one and went to that. Because you probably don't need to write every little one. But again, like I said, like, I don't know, 8 times the last little while. If you ask me what formula to use, you made your own up, right? That's what you do at this point, right? You made your own formula. But hopefully you'd agree, you have all the information you need now to solve, don't you? Right? The applied force was 82. The coefficient, you guys told me, was 0.06. We don't know mass. Gravity is 981. Solve for mass. Okay. Did you already get it? Oh, you did. Okay. So 82. That's an 82, by the way. Divide by 0.06. Divide by 921. So. What'd you get?
139.
Okay. 139 kilograms? That's actually not the answer. Because the sled itself is 5 kilograms. Good catch. All right. So make sure you watch out for the little tricky stuff like that, right? Because this is the total mass of the whole free body object, right? But the mass of the sled is 5 kilograms. So that means that you can really put in a load, like the load that you can withstand is 134 kilograms. Honestly, I actually wouldn't have made a difference when you do sig digs though, because you get 1 sig dig, it looks like. So you'll have to make it 1 times 10 to the 2 kilograms. But I do want to point out, if you have more sig digs, don't leave it at that 139. Make sure that you subtract the 5, right? Watch the little detail like that. Make sense? Cool. Okay, well, just like you've been doing with other stuff then, now we need to ratchet this up to the next level, which is, what if not everything is on this horizontal XY plane? What happens if things are happening at various angles? Okay. One of the questions on your assignment, which is, I mean, really it's overkill for me to ask you that one, but it's the question where, like, you've got someone pulling this way, that way, that way, that way. You know that question there? Right? Where the only reason I'm making you do that is because I really want you to practice how to work with triangles. Because truthfully, you're going to use a lot of trigonometry still. Okay? But essentially that concept applies here, right? What if when you're pushing the box, you're not actually pushing the box straight on? What if the force that you apply is at a little bit of an angle? Can we deal with this twist now? So, where to start? I would say let's draw the free body diagram. This one's already kind of started for us. We have got an applied force coming in at an angle. I'm going to work with that then and say that this applied force really is actually two pieces. There is the force applied in the x direction, right? Because it is pushing it forward. However, there is also a force applied in the y direction. Does that make sense? You're not only pushing the box forward, but you're also pushing the box into the ground. I'm going to say that one more time. You're not only pushing the box forward, but you're pushing the box into the ground. What is that going to do when you push something into the ground to friction? It's going to increase the amount of friction, right? So we actually need to account for that a little bit later in the question. In terms of other things, we've got a normal force, obviously, pushing back up. We've got a force of gravity. If we're pushing the box forward, friction will then be going backwards. So there's our free body diagram. So far, so good. All right. If you're ever stuck as to where to start your formula, just because you haven't done enough examples yet, Newton's second law is always a good place. The net of all our forces is equal to mass times acceleration. We either have to do this vertically or horizontally. And it probably makes sense to do it horizontally, right? Because that's the direction the box is moving, right? The box is not going to go floating up in the air. So we need our net horizontal forces. So that would be the force applied in the x direction is going forward. I know I drew the arrow on this side of the box, but would it make sense that really that is kind of pulling it that way? Right? Like this arrow I've drawn right here is really that way, right? Countering the force going forward, though, is friction. That's your mass acceleration. Okay, so let's talk through how we solve this puzzle. Because really, you have to think of it like a puzzle. This is a big Sudoku. We need to work our way around all the little squares and find out what we're looking for. I need to find the acceleration. That's the question we're solving for. Do I have mass? Yes, it tells me straight up at 67, so that one's good to go. Do I know the force of friction currently? No. So I'm going to need to replace this force of friction with a different formula, which would be U times Fn. Right? However, normal force is normally equal to gravity, but not today. The normal force is equal to gravity plus, I'm pushing down. Does that make sense? So if I want to replace this force normal right here, really the force normal is the force of gravity, like it normally is. But there's also the fact that I'm pushing my applied force in the y direction. That's what my normal force is equivalent to. Does that make sense? Because of the fact that I'm pushing down. You guys follow that? Okay, so let's talk through where we're at from here. Again, I'm making my own makeshift formula at this point. So I still have mass. Can I find the force of gravity fairly easily? How do you solve for force of gravity? Mass times gravity. I've got that. And I have the coefficient of friction, right? What I'm lacking at this point here, though, is my force applied in the x and y direction. Okay? That's what I still haven't put a check mark above. So this is where my trigonometry is going to come in. I need to kind of work off to the side for a bit here. Is everyone okay writing up to this point here, though? So I'm going to go back up to the picture. After you get the hang of this, you'll hopefully be able to speed this process up quite quickly here. It's always one is sine, one is cosine. Okay? And so long as you set your triangle up properly, cosine is always for the x value, and sine is always for the y value. But let's just reprove it here. According to this triangle here, the sine of 20 is going to be the opposite, which is the y value over the actual force applied. And if it's okay with you guys, can I just throw that force applied in as 700 right away here? So I can actually say that the force applied is 700 sine 20. I noticed a few of you go grab your calculators. It's fine for you to find that value, but what I'm going to show you is I'm actually not going to find that value until the very, very last step. Because you've probably discovered that you're getting sick of keeping track of values, especially like you on your calculator. So although you could save this and like find that number, pause on that for a sec, okay? I'm going to show you a different method. Not that it's wrong, it's just another idea. Would it make sense if I just then told you that the FA in the x direction is going to be 700 cosine of 20 for kind of that same rationale? Right? And honestly, after a while, I don't even bother doing the triangles. I just take a quick peek at it and I go, oh yeah, look, this is the opposite, that's sine. Oh, look, this is the adjacent, that's cosine. Right? And after a while, you save yourself some time. Okay? But if I guess if you need me to prove it, it's cosine of 20 is the adjacent over the hypotenuse. So like for Michael, if you have like an older calculator, here's why I suggest that. Now, rather than writing FAX, rather than writing that decimal number, just straight up write it as 700 cosine 20. You know what I'm saying here? Don't put the decimal number in just yet, just write that there, right? What was our coefficient? 0.37. Force of gravity. 67 times 9.81. Then I need to add the FA in the y direction. Again, if you've already found it as a decimal number, it's not wrong to do so, right? But you kind of see how I'm trying to just do this all just in one fell swoop, rather than doing it little bit by little bit, which sometimes gets really tedious, and you're probably sick of it by now. If you can find a way to speed that up, and just do it like, call this 700 sine of 20, and then to get acceleration by itself, when I have all of this number right here, divide by its mass. You see how, like, Michael, I'm looking at you, especially because you got that older calculator, right? You just do this all in one swoop. Now, don't screw up the brackets, right? Because it's very important to. So make sure that you do, like, the whole top of the fraction, press enter, and then divide by 67. Or make sure you put, like, a big bracket around the whole top of this thing here. But you can actually make it so that you don't have to do, like, little bitty calculations everywhere. Again, you can see why I'm saying this a lot. If you ask me what formula you use, this last formula I've written in green here, I mean, hopefully it makes sense as to how I got there, but it really was the culmination of a lot of little steps. Well, this is what physics is. The easy questions are the ones where I just give you one formula and say use this formula. You guys are going to look back at kinematics one day longingly, where you'll say, oh, I only have to use VF squared equals VI squared plus 2AD, and that's it? You're going to be like, it's easy. I mean, maybe you're ready for that point now, where you're like, this is an easy one, because this is where it's going, right? We merge them all together. Well, brave enough to tell me an answer? 4.8? 4.9? You guys are all in agreement? Awesome. Cool. Our acceleration looks like it's 4.9 meters per second squared. That's right. For sig digs, let's say forward, just to add a direction to it. Yeah, for sure. Brief aside here. Hypothetically, if we had a negative value get spit out at us, it doesn't necessarily mean we're wrong, because it is possible. It just means that since I've kind of arbitrarily defined that way to be forward as positive, and this way to be backwards, it could just mean that the thing is moving backwards somehow. Okay, now that's really not logical on this example here, because on this example here, really friction is really dependent on other things. Okay. But if this were like, say, an inclined plane question, you may think that you're going uphill, but perhaps the force uphill is actually not strong enough to actually propel you uphill, and you may be trying your best to go uphill, but you're actually sliding backwards. So don't freak out if you get a negative. You just have to consider the context of the question, because it is possible. On this one here, though, it wouldn't really make sense, though. You know what I'm saying? All right. So let's put it all together. This is like the pinnacle level question that we do here, where we're going to put something on an inclined plane, and it's basically going to have all sorts of forces everywhere. Hopefully you'd agree every time I make a formula, it's all slightly different. There's similarities, right? There's definitely pieces that are the same from question to question, but there's always like a little tweak that's different. And that's kind of, experience helps, I guess is what I'm trying to say. The more you do it, the better you get at it. So this is why I've been harping really recently. Try to do your assignment, because that will really help. The more you get a chance to try questions, the more you'll have experience. Like, oh, I did a question like this before. Because after a while, they are very repetitive. So, okay, let's give it a try. I'm going to redraw this here just because I'm going to want more room. We've got our sled on a hill. I'll draw a box. Okay, what's happening to the sled? The sled has gravity acting on it. I know that much, right? And gravity on an incline, we need to do a little trigonometry. I'm going to change where I wrote that. I'm going to put the FG on this side here. Because we need to break this up into the downhill component of gravity and the perpendicular component. We're actually going to use that perpendicular amount today. We haven't in the past, but we need it today. Why will we need this perpendicular amount? What is it equivalent to? Not friction, normal force. You know how your normal force is normally equal to gravity? But your normal force is actually an angle today, whereas gravity is straight down. So when we want to try to calculate the normal force, which we'll probably need at some point, rather than it being equal to gravity, it'll be equal to F perpendicular. That's all. Okay, other things here. We're going to then have, I'll redraw the downhill force this direction here, just so it's there. I need to read this here. The hill is on an incline. It looks like we're going to try to reach the bottom. So if we kind of take it that the hill is the toboggan is trying to go downhill, we need to now draw friction back up there. And that's one of the things that I don't know that I can really give you a way of knowing that for sure. You have to use like your own common sense to figure out which direction to throw the friction. But hopefully that makes sense, right? It kind of implies that the toboggan is going down the hill, so therefore friction is going up the hill. Okay. Ultimately, the question says determine the length of time it's going to take.
Mr. Bullock, please call 3500.
So starting at the very beginning here, we want to find time. This is actually a kinematics equation. We're looking for time. All right. Well, what other kinematics information do we have? We have a distance of 24 meters. We have an initial velocity of 0.5 meters per second. That's our kinematics information. In order to solve something kinematics-wise, we need one more thing. We would either need to know velocity final, which I'm not given, or we would need to know acceleration. Well, are we accelerating due to gravity when we're on an incline, though? And gravity doesn't account for friction. Does that make sense? So maybe you can see how these are going to be linked here. We are going to need this acceleration. So we're going to come back to this. So I'm just going to leave this kind of hidden off to the side here for a little while. We're coming back to it. Once we find an acceleration, though, you guys do know how to solve for time, right? It's just we need to find the acceleration first. So what formula do we know that involves acceleration that really fits our unit? Good old Newton's second law. Newton. F net equals ma. We need to write a very long, convoluted formula that we're going to have to kind of start here and make up ourselves. So in the direction of travel that we're going, this time around, I'm going to change my perspective. Since we're kind of intending to go down the hill, I'm going to make the down the hill be positive and the friction uphill be negative. Does that work? So the net of my forces is going to be the downhill force minus friction. That's mass acceleration. Okay, well, I don't actually know downhill force. But if you remember how to do this from last day, downhill force is always equal to see how the angle is right here? Know that angle that we have of 20 degrees, which we hopefully remember it was sitting in that corner there. The downhill force is the opposite of that. Opposite involves using the sine formula. So you will memorize this over time, but this is going to be mass times gravity times the sine of 20. Do you remember doing that from last day? I'm kind of skipping over a step. I'm glossing that one. Should I talk about that more? Or do you guys remember doing this from last day as to how to just kind of go directly and say this one is mass gravity sine 20? You're nodding. Okay. When we eventually define F perpendicular then, it will be mass times gravity times the cosine of 20. Okay, so I've got FD. FD is going to be mass times gravity times the sine of 20. But I need to work with the force of friction now. The formula for force of friction is coefficient times Fn. I don't have Fn, but what is Fn going to be equivalent to in this example? Yeah, right? Because the normal force this time will be equivalent to that perpendicular force, which we've never used before, we've never had to, but now we did. So to finally make this formula work, it'll look like this. Mass times gravity times sine of 20 minus the coefficient times another mass times gravity times cosine of 20 equals mass times acceleration. Holy smokes. Again, ask me what formula to use. I mean, seriously, not that I don't want to answer you, it's just how do I start, right? Because it's really, you're putting your own formula together. However, I think we have all the information we need now. We know the mass, 15 kilograms. We know gravity. We can times by the sine of 20. We know the coefficient is 0.05. For the second time, we know mass. We know gravity. We know the cosine of 20. And if I can just skip a step here, can I just divide it all by 15 here? Oh, thank you. I was going a little too fast, wasn't I? Thank you. Good catch. You're right. So our total mass then, this is sneaky, isn't it? I was doing it too fast. Our total mass should actually be 55. Good catch. Thank you. Good job. Okay, so change all my 15s to a 55. Yeah, I was doing it too fast. I'm sure you guys know the feeling. You do like that. Whoops. So grab your trusty calculator. Don't screw up the brackets. You can kind of see why, although normally I'm really picky about units, at this point here, I've kind of given up. So do put units back in later, you know what I mean? But like in the middle of these pretty crazy calculations, I would understand if you kind of drop out of using units. Answer? Anybody else? .89. Okay. Let's go with 2.89. Let me know, Brooke, if you don't end up. Well, we need to not round this number yet, though, because we're not done using it, right? So although you're right, we would make it 2.9. Actually, do we even get that many seconds? No, guys. The coefficient of friction would actually limit us to 1 sig dig. But that being said, we're not ready. We're not done, though, right? So, Michael, read me out a few digits, would you? It was 3 points.
It was 2.894.
Thank you. 2.894. That's enough for now. But you guys all have that value saved, obviously, to use in the future. Okay, so last step here. Now that we have that acceleration, we can now use kinematics to solve for time. Don't you love this stuff? No. Because it really is. I think I said it to you the other day. It's a death by 1,000 paper cuts. It's a whole bunch of small little calculations, right? That's the problem. If you can figure out how to solve the puzzle, you're just doing little steps. But I mean, when you do 20 little steps, if you get any one of them wrong, you get the question wrong. So like, you have to be a machine that doesn't make mistakes. Sorry. All right. Let's see. This is 24. This is 0.5 times t plus 1/2 of 2.894 t squared. Guess what? Quadratic formula. To think, if you weren't in this class, you could be sleeping right now. Okay, it's not that bad. Okay, it actually is. Okay, so take your 2.894 number, you're going to divide it by 2, that's your a value in front of the t squared. Your b value is 0.5, your c value is negative 24. How about it? Negative 0.5 plus or minus 0.5 squared minus 4. Can I just say whatever the a value is minus 24 divided by 2 times that a value, which is half of what you just calculated? I don't have my calculator up, so. You get 2 answers. One is going to be positive, one's going to be negative for, well, all of you guys, really. This is another good example of extraneous solutions, where when you get the negative, you really can't have negative time in this scenario, right? So it's another example of, we've solved something, we didn't do it wrong, but it's not logical when you check your work. So find the positive value, and that should be your time. Don't make a mistake. Don't round anything. Keep your work super organized. Underline, highlight, do little things like call it AX1, AX2, D2, you know what I mean? Like really notate your work, because if you're one of those people who's really sloppy in how you write things down, I don't know how you possibly will be successful at this, right? Like you have to be organized. And even me on my whiteboard, I'm not really as organized as I normally would be. I'm kind of cheating because it's not as easy to write on there. Anybody get an answer? What was that? 4 seconds? Because you get 1 sig dig, right? What did you get before you rounded, just sort of? 3.90. 3.90?
I got 4.1.
Still rounds to 4, which is nice. Okay. Well, let me just write it down, and then I can come troubleshoot anyone who got it wrong. Rebecca, you said 3.90. Okay. Anybody else get 3.90? You did too, you did too? Okay, so it's probably yours expansion then. Is this my last slide, by the way? I don't remember. Okay, good. You guys are probably glad. Okay, so go back up. Okay. So we divide it by 2. It was just negative 0.5 there. 0.05. That's the coefficient of friction though. The 0.5 that I'm using, is that this velocity initial is 0.5. You see the issue there? Okay. Okay, so quick summary of where we're at. I guess first I should say, props to you guys for sticking out physics, because it's not easy. Obviously, this is the kind of thing that only a small handful of people even have the talent to handle, let alone the determination and work ethic to stick out. Because I'm not making this crazy harder than it normally would be. Like this is typically what you're looking at having to do. So, good for you guys. In terms of what I need you guys to build for skills. Mathematically, obviously, that's one big skill, right? Like you have to be able to do numbers in your calculator, no problem, right? But the newest challenge now is you need to be able to like make your own formulas. Right? So the advice I would give is consider the x direction and the y direction, usually independently. Okay? In the x direction, you usually have F net equals ma, and you have friction going one way, you have an applied force going the other way usually, right? You start with that. If you're solving for friction though, now you get the formula UFN, and your normal force is based on the y direction. So now you actually have to make your normal force typically equal to gravity, so then you actually have to solve for gravity as well. Does that make sense? The hardest part is when it's on an angle, because then you have to find the downhill component and the F perpendicular component like we did here. But if this makes sense to you, if you can solve something like this where rather than writing it out like as a number every time, you just kind of save it as mg sine and cosine, after a while you will figure this out. Downhill is always the sine, perpendicular is always the cosine, x directions are usually cosine, y directions are usually sine. Right? Once you get the hang of that, it does get better, right? But then you're just doing a lot of calculator skills. Okay, I guess I'm done. You guys have any questions? Okay. So the rest of today, tomorrow, and Monday, try to finish up that first assignment. And then, do you guys have a preference either way to do the quiz on Tuesday, lab Wednesday, or flip? What do you guys think? Tuesday? Okay. Okay, so we'll do that. Do you guys think at the pace you're going, you'll be able to finish the assignment by then, though? The first one? Okay. Okay, I do have the answer key ready, by the way. So whenever you are ready to mark it, I will get that for you. So, okay. We'll put a pause on this one.